So let me introduce Antoine. To talk about this topic, gravitational waves. So in my other talks you might have seen, he will start from the atoms and then try to deduct the mathematical foundations of gravitational waves. So which is what he called the mathematical voodoo. So let's welcome Antoine.
So the idea is that it's possible in the next 60 minutes to go from knowing nothing about relativity at all to having some sufficient understanding to make sense of gravitational waves. Let's be honest, in 60 minutes it's not really possible, so we'll have to take shortcuts and so on. But hopefully the sorry, is there some?
Take the wormhole.
The what?
The wormhole.
The wormhole. Yeah, that's a good idea. I thought. So I'll take some shortcuts, and hopefully it's all. I'll try and not jump over the more important, like the important conceptual points. I'll try and spend time on, but some of the more, say, purely algebraic computational steps I'll have to skip, and some of the later stuff towards the end I can't give all enough details to be sort of fully respectful of how nice that theory is, but there's just no time. Like in 60 minutes, it's not reasonable. So hopefully it's all sufficiently self-contained while being sufficiently faithful to the actual pretty massive theory that's out there about this general relativity stuff. But that does mean that since most people in the audience, I guess, have very little about physics and maybe like differential geometry in general, I don't know what the level is, but I'm assuming nothing to be on the safer side of things. But if I forget, if I seem to be assuming some stuff along the way that doesn't make sense, please stop me. Like, I'll try and do a path from nothing to gravitational waves that is somewhat faithful to how it actually works. But if I seem to be pulling rabbits out of a hat, please stop me if there's like stuff from geometry or physics that it doesn't make sense to you. So the nice thing about general relativity and like relativity in general, like Einstein stuff, is that I think I can safely assume you've all heard of it before, right? And you probably have all heard about this sort of heuristic, like intuition for what's going on in terms of, let's say we can summarize sort of general relativity. Well, let's say it's sort of the catchphrase you'll see in, say, vulgarization journals, like kind of popularization journals, will be something along the lines of general relativity tells you that we live in some space-time that's curved, and not only that, but it's curved by, say, the Earth, black holes and stuff, it's curved by matter. So this is the sort of slogan that you hopefully have heard before. And the goal is to try and explain a little bit what's the underlying theory behind this, and sort of we can think of general relativity in many ways as just apply differential geometry. So we'll kind of talk about differential geometry along the way to make sense of things like, well, why do we have, first of all, why should we have space-time playing around, not just space and time? Why do you have to combine them together in some way? Like, why do you have to combine them together from the physical perspective, and then how do we do that mathematically? And then same thing with curvature. Why should we live in curved space-time? I mean, it looks pretty flat around here to me, but apparently we live in curved space-time. So why is it that physically we want to postulate that? And how do we encode that mathematically? And same thing here. Why is it that the curvatures have anything to do with matter? How do we motivate that physically, and how do we encode that mathematically, let's say? So that's kind of you can think of the goal of the talk as sort of explaining this a bit more from sort of the point of view of differential geometry, which is what's used to formalize general relativity anyways. And towards the end, then we'll see as a sort of pretty much a quick corollary that actually there's such a thing as gravitational waves that should occur. I should point out the reason why I'm talking about this and not some of the stuff maybe closer to what I actually do in research is because gravitational waves were actually observed this year, and it's really cute because Einstein published this thing in 1916, and then 100 years later this year they actually found experimental evidence of it. So it's a really nice story, say, of scientific achievement in general. It's really, like, the timing is impeccable, which is very ironic given that, time is relative and so on. Alright. So, as promised, let's make sense of all these things. Let's say one at a time. First, why do we have space-time? Why not just space and time? Okay. I'm going to stop talking about that over here. I want to try and have all the main points here by the end. I might have to start writing smaller, but hopefully then we have the whole picture here. So why would we want? Well, we don't want to say, what is the physical motivation for saying that space and time have to be combined somehow? Well, let's take a step back and think, how do we describe this mathematically? The simplest answer, and the first one anyone would write down, is say, well, and that's what is attributed to Aristotle from a while ago. I mean, he didn't say it on those terms, but essentially he said, well, space-time is just space and time. It's something that looks like R3 and R. Surely that should work. Well, not quite. It doesn't quite work, and for a very simple reason. If you picture, say, why does it not work? Well, because people can't exactly, in practice, this is not what you observe. It's more complicated than that. Because think of the following situation: if there's someone, say, I'm sitting on the train platform, and someone is on the train leaving the platform, and say they're flashing a light at me, then we both agree on the time at which the flashes occur, but we'll disagree on position, because I'll say, you're going away, why are you running away from me? And he'll say, no, I'm not doing anything, I'm just standing there, you're the one who's going away, right? So and this is the first hint of relativity, like observers, see, the physical world, we observe it, so observers cannot agree on both position and time at the same, together, right? There's something more going on. Just for a simple example of someone moving in a train, is going to say, no, I'm standing till you're the one moving, and you disagree. So we have to worry about, it's important, we have to really take into account who's observing what, right? So how do we encode that? How do we describe this? And this came much later, and this is attributed, roughly speaking, to Galileo, who said, well, it's a more complicated picture. It's really just that we have something like the following. You have some, so space-time is going to look like R3 crossed with R, but only from the perspective of observers. So space-time is really going to be, okay, first differential geometry terminology. Space-time is really going to be some four-dimensional manifold, and manifold just means something that is locally like Euclidean space. So manifold is essentially just some topological space that's locally homeomorphic to Rn. You need it to be like Hausdorff second countable, that's technical. The point is, the manifold is locally homomorphic to Rn. Like around every point you can find a neighborhood that is homomorphic to Rn. So the simplest example of a manifold is the one we live on, is the sphere. It's locally flat, I can't see curvature here, but it's overall, it's only local, right? So that's what Galileo says space-time is. It tells us it's some four-dimensional manifold, 3 for space, 1 for time, and we can only identify it with R3 cross R once we make a choice of observers. So this guy, you can think of an observer, and the observer will simply be sort sort of encoded, the notion of an observer will be formulated as just a smooth map from your manifold, a smooth diffeomorphism, so the map is invertible and the inverse is smooth, from the manifold to R3 cross R. Right? It's just, it's sort of, basically, if you just look at, sorry.
What kind of manifold? It's like reference frames cross R3 cross R.
Well, so like once you fix an observer, M is diffeomorphic to this, so it's really the same. So like geometrically, it's the same manifold as R3 cross R, but it's just that let's say think about this. When you're saying anything physically relevant about this, you have to worry about which observer you're looking at. So let's say if you fix an observer, space-time is just in the Galilean framework. Space-time is just R3 cross R, but if you want to be able to describe precisely what happens when someone is on a train going away from you, but from their perspective, you're the one moving, you just have to throw this on top. But here, so far, there's no space-time is still flat, it's still R3, it's still diffeomorphic to R3 cross R. There's no curvature, it's just pointing out, this is kind of the first step in saying, actually, we have to be careful about something else. The space is not just like this. It's if we want to say physical things about space, we have to worry about which observer is observing it. Is that answering your question, Ross?
So it's just like M is R3 cross R with different coordinates, right?
Yeah, think of it as like this guy could be really drunk and forgotten where the origin is and just think things really blurry kind of thing, right? Like pick your favorite diffeomorphism of R3 that's really weird and that is technically diffeomorphic. So it's just, think of it as just choose, okay, the simplest thing is choosing...
It should be a constant velocity thing, right?
That'll come next,
okay.
yeah. That'll come next, that the observers will look at have to be rated in the right, like have to be, yeah, that'll come in a second, basically. Did someone else have something?
You actually answered my question.
So, that's yeah, so as I'm already sort of, let's say, we have to work, like, as you pointed out, we have to worry about how to go from one observer to another. But I want to say one more thing about just this first. So, I want to say the following. So we postulate, essentially, how do we make sure that these observers are related in sensible ways? So we have to make sure of the following. So we have two things. So we have observers like this. But remember the motivating example of someone on a train and someone sitting on a platform. We can agree on when the flashes of light occur, but we can't agree on who's moving. So people, you still agree. Observers can still agree on the simultaneity in time, but not in space. So to encode the simultaneity in time, you basically say that you have some projection along the time thing, such that the observers agree on that. And the way you encode, you say that is just you're going to say it like this. So you have M here and R3 plus R there, R here. So your projection sort of picks out an absolute reference for time, and then your observers, they have to, whichever observers, they all pick out, they all agree on time. So if you take a projection like a second coordinate, when you do this, like observers agree on, this is just fancy way of saying observers agree on time. So the point is, observers agree on time, and then distances, they don't agree on distance, well, they don't agree on the position of things, because one on the train, I'll say I'm moving, I'll say he's moving. But what they will agree, if I'm standing there and someone's going on in a train, we'll agree about the distance between us. Right? He'll say, I'm standing there, you're moving, I'll say, I'm standing here, you're moving, but we'll both agree that there is distance between us, and we'll agree on the value of that distance. So the point is, these observers will still agree on so observers agree on time. Let's say agree on time. And we also have that, let's say, for any point in your manifold, if the point, let's say, think about those flashes of light. If two observers, let's say, if two observers say it agrees at the, two observers agree that this event is happening at the same time. Well, okay, this is not the best way to write it, but okay. If they agree on, amongst all observers that agree on time, then let's say the distance, so if you project along the first coordinate, the spatial one, they'll agree they'll have to agree on that too. They don't agree on absolute position, but they'll agree, let's say this thing is constant, they'll agree on relative distances. The point is this, the point is that this is still formalism that does not have sort of space and time intertwined in any way, because you can measure time first and then distances second. They're completely separate from each other. There's no connection there. They're still completely separate. And then essentially the way to talk about the basic postulate then in physics will be that the laws of physics are independent of the observer as long as they're related by either a translation in space, a translation in time, or just a constant motion in space. And that'll be sort of how you go from this to having physics.
I'm a bit confused about how this is quantified.
Yeah.
So we're sort of assuming that all the observers agree on time.
These two things are given.
Okay, so then this is saying if two observers agree on time.
Yes.
Then.
Well, not constant. It's independent. The point is, it's independent of observers. Once you fix for a point in the manifold, as long as the two observers.
Yeah, they're agreeing with time. But it cannot be like.
Oh yeah, no, but this thing, yeah, you know, but this is silly. This thing you already know. Basically, the point is this is independent of.
But you can't even have like both things agreeing on time, but one like moving away from the other.
Yeah, but if one is moving away from the other, then so if I'm standing and the guy in the train is running away, I'm the first observer. But when he's the second observer, he's standing there and I'm moving away. So whoever measures the distance, we measure the same thing. Yeah.
Okay.
It means that the observation does not depend on the observer.
The observation of distance does not depend. The observation of position depends, but relative distance doesn't.
So you're basically saying that that's like the constant is the distance between two observers.
Yeah, so constant meaning independent of the observers. Like if whichever observers I pick, they measure distances in the same way.
But not in time.
What do you mean?
Well, because the way you write it in the second part is still time.
That-
Oh no, yeah, but that should be a one. Is that what the?
No, but yeah, I got it.
Yeah. It's just yeah. So, but then I went all the way around. Andy, are you?
I'm a little bit confused about all this. I'll think about it.
I mean, to be honest, all of this is really like massive battery math. It's not really useful. It's just a prelude. It's time to like not jump straight into the special relativity stuff. It give you like an intermediate step before that. I have to like all of this. No one really uses. It's kind of more as a motivation for where it kind of. The moral of the story is it's important who's the observer, and that will be the starting point of then special relativity stuff.
Okay.
Do you have something else?
Just make sure they understand.
Yeah.
So we don't really need data sample.
No, we don't need that. No,
Okay.
that was from.
Okay, so we're all.
Yes. Yeah, so this is written in a stupid way.
Got it.
Yeah, this is right. Whatever observers I look at, they measure this. This is what I would try.
I mean, like, when I say it's constant, I don't quite get it, like, it's constant with respect to...
It's constant with respect to alpha and beta. It's independent of the observer. It's not constant. If the guy's in the train, the distance is changing. But the point is, if somehow, see, if it's me, if I'm alpha measuring it, the guy in the train is beta, if there's someone else somewhere, say on the plane, that's measuring the distance between us, they'll also measure the same distance, for example.
But, like, what you mean distance, like, you actually, you have to have 2 points in space, but let's say for
yeah.
P and POE, and such that the time span is the same, then the projection onto space and the distance is the same. And
Yeah. Okay, so this is why it didn't go well because yes. Okay, instead of blah.
I guess what you want is for any P1, P2,
Yes.
such that The second projection is the same, then for any alpha and beta, the distance is the same. Yeah, there you go. Then for any alpha and beta, exactly.
So that's why they're missed.
Just
Because
alpha for both of them and independent of alpha.
Yes.
Okay. That makes more sense.
Yeah. Yeah, the point is no one uses it, like, took this out and got lost in it. The point is the interpretation is important, the more formalism no one uses. Okay. Someone else? Did you? Moral of the story, who makes the observation matters a lot. Now, here we're not getting anything new out of that, because we haven't pushed, we're saying, okay, who, like, see, I kind of preluded it saying, if, like, all observers, as long as they're related in a nice way, meaning that either they differ by a change of the origin or by a constant motion, then the laws of physics should be the same, yeah?
Actually, question, I guess kind of a non-mathematical question here, but why did Galileo kind of determine that we need the manifold structure and not just the R3 cross R structure? What was the observation that said, hey, we actually...
I don't think Galileo used the word manifold.
Well, when we're thinking, hey, we need to actually talk about curvature of space-time.
No, Galileo is not saying curvature of space-time. Galileo is saying worry about the observers.
Okay.
And then there's something on top of that. You combine, you say observer, like who's observing matters, and then Einstein comes in and says something else, and those two give you that you must have curvature.
Okay.
Yeah,
Sorry, I got
he did not talk about curvature.
manifold and I was
No,
thinking-
he did not talk. Yeah. He didn't talk about curvature. He didn't push it sufficiently far to get to curvature. Because the thing is the following: if we're saying that two observers that are, for example, that just differ by how they pick the origin in R3 cross R, well, yeah, which origin they pick, for example, then the physical, like experimentally, physically, we don't see, there's no difference in the laws of physics if I'm here or if I'm standing in a train going at a constant speed. If I drop the chalk, it just falls straight down. The laws of physics are the same. So the point is, if the laws of physics are the same, there's, in particular, there's one very important law of physics, which is, interestingly, came just before Einstein, like Maxwell derived it just before Einstein, is the fact that the speed of light, which comes from electromagnetic waves, which is the stuff that Maxwell was doing, the speed of light must be constant, because if I do experiments, I measure it to be a constant. So I'm saying the laws of physics are the same for all observers, so it must be constant whether the observer is standing here or moving on a train, right? It should be the same. And that is the second thing that if Einstein says, see, Galileo already said we have to worry about the observer, Einstein will say, let's worry as well about the fact in particular that the speed of light has to be constant for each observer, and then if you combine those two, you'll get curvature. That's what that's the contribution that Einstein made. That means that he gets something highly non-trivial that Galileo did not see, or did not, he made one more assumption, so you can more stuff out of it. So that's exactly, let's see this now, how do you get from laws of physics are the same for observers plus speed of light is constant to somehow space, time, and all that stuff. Like why do these simple things give you something so surprising? So Einstein comes along and this is what he says. So so let's just to summarize, Galileo says observers matter, and then Einstein comes along and says well, he says the same thing, but he really pushes it all the way in the sense of, well, observers matter. In particular, the speed of light has to be a constant for all these observers. And now let's see how from this two simple postulates you get something surprising out of it. So just so that I can draw the picture and so it's easy to follow, let's just think about just one spatial dimension, one time dimension. So I have someone here, and say he has coordinates x and t. So if my coordinates were something like 1 meter here and 1 second there, because the speed of light is so fast, then as soon as it goes 1 second, it goes over enormous amounts. It would be something practically thought it would be silly. So I rescale the axis to just have the speed of light being essentially 1, just to make it clear what's going on. So then if at time 0, so if I'm the observer here, at time 0 I just flash a light, like I just turn on a flashlight and just a flash, then this is the trajectory that the light does. Okay. So, but now, of course, there's two postulates we made. One was that observers matter, the other one was about the speed of light. So I have to introduce another observer, otherwise I'm not getting anything out of this. So let's say that there's someone else that starts initially, another observer that starts initially at the same place I am, but then he moves away from me very, very fast. For the purpose of clarity here, let's say he moves away at a speed like half times the speed of light. So then what is this trajectory going to look like? That should be halfway through, halfway in the middle. It's going to look something like this. That's going to be a trajectory. Okay. Now, okay, this is, let's say t tilde, for that's, see, that's his, that's his like x tilde equals 0 axis, that's where he is sitting, right? So that's his time axis. The question is now, where is going to be his x tilde thing? Where is going to be his, the line corresponding to what he sees as time being equal to 0, like where is that going to be? How do we figure this out? Well, the point is the speed of light is a constant, and here I set it to be equal to 1. So wherever I put his x tilde axis, it better be such that the angles here are still the same, because in this in this frame, like to him, this just looks like that. This is just like x tilde t tilde, and he has the speed of light here. He has the ray of light here. So to him, this looks like that. So to me, it better look like the angles are the same here, right? Does that everyone buy that? Because that's, yeah, no. I mean that's simple, but this is basically the only place where we really use the fact that the speed of light is constant in any reference frames, and that will lead to surprising things. So it's a simple observation when stated in those terms, but it will have interesting consequences. For example, I mean the best thing is this. Let's try it again so it doesn't get too crowded. So let's look at what happens in his reference frame, in his coordinates. What happens there? Well, he sees the ray of light like this. So, for example, if he looks at the coordinates of this point, let's say he draws these two lines in his coordinates, what do these two things look like in here? Well, this is parallel to my x tilde x to his x tilde thing. So it's some line of also constant time, so it better be again parallel to the x tilde one, so it better be parallel here. Or parallel. So this was a dashed line. From there, and same thing with the other one, it's going to be parallel here. So that's what he sees, that's what I see. But then the funny thing that happens is that he's just seeing a square, so this area here, let's say if it's moving, I don't know, let's see epsilon. Then this area here is just epsilon squared. So what you should think about when you look at this is that relativistically speaking, this thing is still a square. So this is what looks like to me as obviously not a square. It's still relatively speaking a square because essentially these two here are still right angles because of, again, this constant of the speed of light. The right angles are now these things that are at the same angle from the path of light from, yeah, if the t and x axes are, if two axes are at the same angle to the path of a ray of light, then this angle here is really, relativistically speaking, a right angle. So by the same reasoning, this is a right angle too, and then if you play around with this, well, these things, this is going to be a right angle too, actually, and so will this one here. Relativistically speaking, these are right angles. So, moral of the story, if this is epsilon, then the area of this thing will again be epsilon squared. Do you buy this?
You say from the point of view of observer 1.
Yes. Do you buy this? Because if that's the main thing, like the rationale follows from like basically a version of the Pythagorean theorem, but where the angles, the right angles, don't look to us like right. Yeah.
I'm lost. I got lost when you said they're right angles relativistically speaking.
Yeah.
But they're not right angles to observer 1. So how can you conclude
No,
it's a
but-
square
but
to
there's-
observer 1?
Oh, so the only thing that you did with C was to draw a line bisecting the angle, right? And then besides that, you're just applying Galileo to everything. You're just saying whatever 2 measures is whatever 1 measures.
Yeah, yeah.
That was about X distances, not, I guess,
So whatever he measured in the right angle, then 1 should be measured. So pretty much what he's saying is that your intuition is fucked up, so it doesn't look like that, right? I don't know. Is that
Yeah, intuition is fucked up is a good way to start. No, but this is exactly what's going on, right? It's back to what's from before the distances they agree on.
So I'm okay with the T tilde green line.
Yeah.
I'm struggling with the physical interpretation of the X tilde.
So x tilde is it's a tilde equals 0. It's like the stuff that this observer see that's happening at this time.
So we're supposed to
0.
think of this linear algebraically, right? As linear combinations of time and space. If I take a point on this thing, the observer 2 sees it as its coordinates in the T tilde and X tilde.
Yeah, it's a general coordinate.
As a base, as a basis.
Yeah, yeah, it's a general coordinate.
Not like,
Yeah.
don't, yeah, I mean, yeah, you just project down onto, they're not orthogonal, so you don't just project down. You write the linear combinations, you can't just project because they're not orthogonal in my reference.
Yeah, it's a change of coordinates, right? We're looking from how observer A sees observer B's thing, so we're changing coordinates from basis B to basis A. Yeah.
Is there a reason why you want to preserve the epsilon squared quantity?
Oh, at this stage, no, not necessarily. It's just that then from this thing, we'll see why now, like the distances in time and space have to be related from this.
Has to be
Like epsilon squared does this. There's no relevance of epsilon squared right now. Like in a second, you'll see why it matters, why, but right now this is not. It'll just you'll see in a second. Yeah.
Okay, so I based on what's written on this board, I agree. I think I'm just confused by the way that you're drawing this parallelogram and then telling me that it has area epsilon squared.
Yeah, it's okay. So maybe let's cheat and say ultimately what we're going to do is we're going to say the metric is not the metric we're used to. The way to measure distances and angles and areas is not the one we're used to. So think of this as a prelude, as saying surely the area of this cannot be epsilon squared, but it is because he clearly measures it as epsilon squared, and the observers agree on at least relative like distances and
The whole thing is that we're applying Euclidean geometry intuition to Galileo plus Einstein. That makes no sense.
It's like saying the angles on the sphere should add up to 180, but we know they don't, and it looks really weird, but they don't. Right? The point is, yeah, if you draw a triangle on the sphere, or like North Pole, and then on the equator that has like 90, 90, 90, like 3 right angles, that doesn't make sense, but it's true, and it's right. Like that's the whole joke of like the polar bear. Like if a bear goes south, then east, and then north, what color is he? Like if he goes like south for like 10 miles, then east for 10 miles, then north for 10 miles, where does he end up? He ends up at the same place. The bear has to be white, because the only way to do that is to be starting from North Pole.
Yeah,
right? Yeah, no, but to the whole, no, but to the point is like, no, but I know exactly. But the point is, if I try and draw something like that, you're gonna say, well, no, that's not. These are not right angles.
Okay.
But you know, in the sphere there are. The problem is, okay. So here's the thing. Ideally, I would have the. I would have like, if I had a model sphere, we could agree on like the angles of the sphere. If I had a model of this, then we could just look at it and say, oh yeah, in this warped geometry, they look at right angles. They are right angles, except to us, they don't look like that. It's something that it's like right angles on the sphere that don't look like right angles to us.
Okay,
Yeah. I mean, it's not meant to be intuitive at all. But the important thing is that it's simple once you make the right postulates. Okay, so is everyone buying that the area of this thing is epsilon squared? Yeah. Okay. Well, I should have asked the other question. Is anyone still confused?
Is that an
No?
axiom? Is that an axiom?
Sorry?
You are proposing an axiom?
I'm not proposing an axiom. I said the axioms are observer measure like the same relative distance and stuff, and the speed of light is constant. From that, it follows that this thing that does not look like a square is actually a square and has this area there, right? That was what I was hinting at in the abstract. It's like simple postulates plus actually just a change of coordinates give you some really surprising stuff. That's the story of all these things in relativity. So now, yeah, let's see. So you're asking a good question about why do we care about epsilon squared? Well, let's see now. I'll just basically the algebra is like one line now. So let's summarize what we have. I have this thing here, and then let's see this and that. And now let's add these things in. Okay, so I should keep the colors. This was the light, and okay. And what do we have? We have this. This thing is just length epsilon. Okay, and so now let's look at this. So let's say that so the punchline will be that things are different to the Galilean case. In the Galilean case, I could measure time intervals and spatial intervals independently of each other. But in this case, it will turn out that it's not that time intervals and spatial intervals are like independent observers on their own. It's some weird combination of the time interval and the space interval combined together. That thing will be independent, but not each separately. So, for example, if I want to look at, say this, so this is x0, right? This is some, well, let's say delta x, some spatial interval, and let's say here, this is say delta t, right? This is sort of like spatial intervals that the guy in x would measure. Now, if we just look at this, let's just what we're gonna add up. We're gonna compute the area of this thing in two different ways. Well, one way is to say it's just delta x plus delta t. Oops, delta t, the whole thing squared. Fine. But the other way to do it is to add up, for example, this epsilon squared. And then what else am I missing? I'm gonna add up these two pieces, which is just delta t, so 2 delta t squared. And then I have 4 of these right angle triangles, so I get 2 times delta x delta t. So epsilon squared plus 2 delta t, sorry, delta t squared plus 2 delta. The important thing is these things are equal. I just computed the area in two different ways. Okay, now let's do some basic algebra. You get what? You get blah plus this plus your delta t squared. So yeah, these two things have to be equal. So then simplifying things, you'll just end up with basically delta x, the important thing will be this. The delta x minus delta t squared will be equal to your epsilon squared. So that's where the epsilon squared comes out, because the epsilon squared is a constant for those. But this tells us that whatever your, well, no, it tells us that for the way you measure distances and spatial intervals and temporal intervals, they're not necessarily constant by themselves. If they're written this way, then they're constant. The point is, if you had another frame and we would draw a much messier picture, not like this, but say, if I had some observer, let's say was going at some speed like this, for example, and he was looking at the same point here. The point is, if I look at this lower triangle, if I have another observer that has, say, coordinates delta x prime and, well, measures intervals delta x prime and delta t prime, they'll still measure, and then I complete the thing and have like the square again. You'll still measure the green part inside to be epsilon squared, and I can still do the same computation, and so I'll get that this delta x tilde x squared minus delta t tilde squared equals epsilon squared. Again, because these weird things are actually squares and they have 4 right angles. Does that make sense? The conclusion is that actually I don't have, see in the Galilean case I just had delta x was a constant, was independent of observers, that delta t was independent of observers. In this case I do not have that, but I have that delta x squared minus delta t squared is a constant independent of observers, right? And that is, well, that is very, very weird, right? This is absolutely bizarre. There's no reason to, no one's going to write down and say, oh, obviously this is true. But we will write down, well, observers matter, and the speed of light is constant, and then it follows by just elementary geometry, well, non-Euclidean, but elementary non-Euclidean geometry that this is true. So, yes?
So, could we write down that delta x squared plus delta t squared is equal to epsilon squared?
Delta x squared plus
plus
t squared?
From that triangle.
From, how would you?
From right angle triangle.
Which one? Where?
The lowest one. Yeah, just.
Yeah, but no, it's not exactly. Okay, that's a very good question. In the relativistic setting, it's not gonna. Let's see. Yeah. Okay. Yes. So the answer is you can do it. You can do it. In this case, you can, sure. But if you move it to this guy, then you can't do it anymore. Or if you yeah. Because the point is, if I were to look at a different observer, then we know that the angle between the x and the t things has to be such that the light cone is like the light path is always in the middle. So it would tell me that it would tell me that I can still have like squares here and so on. But for these guys, see now these guys, I don't think. Let's see. Yeah, we're not gonna. I don't think we'll be able to do it in this case anymore. Like for some other observer where we don't have this coincidence here. Is that true? Yeah. Is that convincing enough or not? No. What's a better explanation for this? Let's see.
What was it?
The question was
like, why don't you just look at this one and say, well, by usual Pythagoras thing, this delta t squared plus delta squared is x epsilon squared. Yeah.
Just for this particular case, should epsilon be 0?
Why?
In the green frame, epsilon is 0.
Why is it 0?
Well, epsilon squared is 0. If you postulate that delta x squared minus delta t squared equals epsilon squared. Because in the t frame you have delta x and delta t.
Oh yeah, okay, that one, yeah.
So but then that doesn't match this picture where delta x doesn't seem to match delta t, right?
Doesn't match which picture?
This picture, delta x delta.
This one? Oh yeah, okay. Yeah. So. No, you're right. It doesn't measure. I mean, but it goes back to the fact that this thing here is a square, but it doesn't look like a square. So I can sort of like. The point is, of course, I cannot pull off a construction like this and say that the area of this thing in the middle is epsilon squared if I'm looking at Euclidean stuff. Yeah, I mean, like all I'm doing drawing the other picture here is, you know, like adding these things and so on. Did I answer your question or not?
So is it the case that in both frames delta x equals delta t? Or plus or minus delta t?
Is that true? This example, maybe. Sorry, Gio.
Yeah, I'm confused. Because I guess I'm confused by the so I understand we're saying the speed of light is constant, but the other principle that we're starting with, because I know, I mean, like relativistically, if you measure distances and you're moving near the speed of light, you'll get a different distance.
Yes.
You'll measure different. So that can't be what we're saying is true, right? That can't be what we're holding to be a priori true, right? Because we know at the end distances are going to change if we're in a different reference frame, right? So what is it that we're actually holding fixed here as we go between observers?
Yeah, so let's see.
Shouldn't that be the speed of light?
Well, I mean, other
yeah, that
like
definitely are.
like how do we, go?
Right, I see. But okay. So you're saying we're not taking the fixing. I mean, okay, there is one thing though with the whole speed of light and distance shrinking. I don't think this maybe answers fully the question, but some of it at least. These observers measure the same thing is only true if they're moving at constant relative speeds. And a lot of, for example, like the twin paradox stuff we hear of is because he's accelerating really close. So like this doesn't account for like it's when acceleration occurs, that's when you get these like sort of time, like the twin paradox. Like if you're going really close to the speed of light, you're coming back much stronger than the train that stayed on Earth. And this is when your acceleration plays a much weirder thing. Like it's the thing that's gonna mess you up. I don't think that's the full story, but it's like saying the way we measure time and things change. Yes, ultimately when we throw acceleration into the mix, but for things moving at constant relative velocities, like, cause okay, you're saying we know that these time intervals will shrink and stuff like that. Yeah, but in context, we're also throwing in observers accelerating away from one another. I think is partly one of the things that's going to mean that, well, then it's not true anymore that they measure the same distances because they're not moving at constant speeds relative to one another. I think that is one of the things that, we're postulating the distances they measure are the same for two observers that move at constant speeds relative to one another. And so if one of them is accelerating at some point, then that starts to break these. Of course, these postulates they don't measure the same distance. There's part of that that's going on. That's kind of a cop-out because it's not the whole story, but it's you cannot get to these. Yeah, we're restricting how observers must be related in a quite rigid way. It's the reason why we can make such a bold claim as they measure the same distance in the same way. Like what?
No, I thought I could know. Because I think like Adrian does have a point. You can be moving at constant speed, but if there is a bar approaching you at really high speed, it's going to shrink anyways. It's going to cut. So what's epsilon again? I think the whole question is what's epsilon. If we can see that whatever epsilon squared is in the tilde thing,
I think the question is what's being preserved.
Exactly, yeah.
From
Yeah,
observer to
yeah.
observer, because
Yeah,
if
be-
not.
because I think it's not the epsilon squared. I think it's not that whatever 2 measures epsilon squared is whatever 1 measures epsilon squared is that thing is constant for whatever frames. So, but I'm not sure. Because
What's
yeah,
that curve
you
look like? X squared plus d squared equals epsilon squared.
one of these
Yeah.
equivalent.
It's gonna be a hyperbola.
So you should just be able to show it. It's invariant under this transformation. You should just be able to see the coordinates the same. I guess it's not inspiring to show that it holds, that it's invariant. It's more inspiring to derive it from some reasonable exercise.
I mean, so the thing is this, in general, if you see this in like a first class on like special relativities and stuff, it's just a linear change of coordinates, so they just
Yeah.
painfully take half an hour to derive the change of coordinates you have, and then you do some algebra, and then this thing comes out to be a constant.
Yeah.
The goal was to not spend 30 minutes doing the tedious algebra and instead give a quicker derivation. I guess there's too much kind of lost in transition in the middle when actually it's not as clear, but yeah, you can. Sorry.
It's actually, I think, a relevant question. Does the curvature should come up in special relativity alone?
No, this is just justifying. So we had the first line was space-time is curved by matter. This is justifying why space-time, why space and time are not just
why they're
completely,
intertwined.
yeah,
Okay.
why they're not completely disjoined and why they're intertwined. The point is we can't measure relative distances and relative spatial and temporal distances independently from each other. This is just justifying why it's space-time, not space and time. No, it's not really curvature. Well, yeah, it's not really curvature at this point. Yeah, it's not the curve. Yeah. The curvature comes from throwing in something else, like assuming something else. Okay, we're never getting to gravitational waves. Well, I can ask for. Well, I don't know. I was gonna ask. No, are people convinced? No, they're not. So.
Well, you can take as an axiom that whatever you do actually those squared is constant, then sure.
Yeah, so think of it this way. If you can think of it as just it's a linear change of coordinates. You go through the painful algebra for half an hour, and then it turns out that the way these things transform, this is constant. Okay. And forget about the rest of that. Okay. What is the bigger picture here? The bigger picture is that we assume two things. We assume that the laws of physics are the same in all reference to strings, and so in particular the speed of light is constant. And from that and simple but poorly written algebra, sorry about that. From simple derivations, you can get to the fact that actually spatial and temporal distances are not preserved independently of one another. It's only this quantity that is preserved for all observers. So the point is, this simple assumption, and well, obviously math voodoo that I don't understand sufficiently to explain it well, leads us to this surprising thing. To go back to the motivation, the general underlying thing. So. Go back here. The point is, why not space and time? Well, because of two things. So, yeah, I mean, essentially, let's say c is a constant, speed of light is a constant, plus essentially a change of coordinates. So this, let's say, this postulate plus this will give us that. This is the takeaway message. If we assume speed of light constant in all for all observers, as long as they're related by just translation of the origin or by constant motion, then just doing change of coordinate gives us that actually we have space and time intertwined through quantitatively precise distance. Okay. So in about 50 minutes, we answered one of the three, well, we described one of the three things thrown out there. We still have to talk about dealing with still talk about curvature and why curvature has to do with matter, and then from that you put all these together, you shake well, and then ta-da, gravitational waves come out, right? But yeah.
So C is constant. That holds for people that are only moving in constant velocities with respect to each other, or C constant no matter what.
Yeah. For observers that are moving, constant velocities with respect to one another. Not if someone's accelerating, then this doesn't.
C is not necessarily
No.
constant.
No. Yeah, it's
So acceleration's not relative.
Yeah.
I'm accelerating no matter what. If I'm accelerating, I'm accelerating.
No, accelerate. Yeah.
Right. Think about the elevator experiment. If you know if your elevator is moving, even if you can't see outside the elevator.
Or think about a cup sliding along a table. If you're moving along with the cup, you'll see the water in the cup. It'd be very bizarre, even though it should be stationary.
This is not nice.
I'll be clear,
My water is moving backwards too.
We get nauseous.
Okay.
Yeah. Okay. So in 8 minutes, what are the important? Sorry. Well, no, but I mean. What?
You can make this a series of grad student seminars.
Yeah.
Make this a lecture series.
Really, you want more of this every week?
Just when we start typing this
We won't have a
Sorry.
speaker.
Yeah, make it
So
serious.
yeah.
I don't know.
Agents for questions, contact expert.
I mean,
Professor.
no, but yeah, like in 8 minutes, how do what are the more
Well,
important?
there's one option. We either skip that one and do gravitational waves without knowing where the curvature came from and just assuming it, or we do this and then we don't talk about gravity.
Actually, do talk about curvature and let's
Yeah, do as
do in the
a
future. Maybe in the future.
yeah, do as a go.
Just keep going.
I'll do the rest in 8 minutes, 7 minutes. It'll work fine.
It's a debate.
All right, so look, you're not even a grad student. If you're complaining. So, okay, why curvature? Okay, so again, it's going to follow the same recipe of. I don't know if I'm going to write much more down. It's not like it's going to be the same. Like why curvature is going to be. It's going to come out of a similar thing where we're making a physical postulate plus essentially again just a chain of coordinates, and that gives us that well actually curvature has to show up, and curvature has to do with matter. The physical postulate is the following. In just like Newton, like in basic physics, you can think of them as just caring much about basically like constant of proportionalities between things. Like if I have an electric field, how does the thing change? Well, the proportionality constant is the charge. If I push something, how does it move? Well, the constant of proportionality between how much I push it and how it moves, that's just the inertial mass. If I have a gravitational force acting on something, acting on some chalk, the way it falls, the relation between how it falls and the gravitational force acting on it, that's again just a constant called the gravitational mass. Okay? So you just kind of compute these things experimentally. And the really, really bizarre thing is that it turns out that experimentally, it's impossible to distinguish inertial mass from gravitational mass. And that's the really cute things you can see if you have this is probably there's a YouTube on this of if you have a tube with vacuum inside and you have a feather and a rock and you drop them, they go at the same speed, right? The only reason if I did the experiment now that the rock goes down faster than the feather is because of air resistance. If there's no air, if the only thing acting is actually gravity, then they go down at the same. If they have the same mass, of course, they go down at the same speed. So the point is, experimentally, we cannot distinguish a gravitational mass from inertial mass. Experimentally, we cannot. So Einstein says, well, then they're not different. They're the same thing. Gravitational mass and inertial mass have to be the same. So what does it mean? It means that, and this is you mentioned the elevator experiment. So this goes now. This is exactly where we go next from this. So if inertia is the same thing as gravitational acceleration, it means that I cannot distinguish if I'm just standing here with a like 9.8 acceleration, like drawing me towards the center of the Earth. I cannot distinguish this situation, doing any physical experiment, from the situation where I'm in a spaceship, really, really far away into deep space, far from other other masses, there's no gravitation, I'm far away, there's no gravitation, but my spaceship is accelerating at 9.8 meters per second squared. If the spaceship is accelerating at the same, if the inertial acceleration is the same as my gravitational acceleration there, Einstein will postulate I cannot make a difference, I cannot see a difference physically doing any physical experiment between these two situations. Yeah.
Was there ever a point where people thought they were different? I don't
Well, there's no reason. Why should it be the same?
Well,
I mean, one is how it resists to me pushing it. The other one is how the mass of it, like they are attracting each other via gravity. Like in the sense of why should the electric charge be? If the electric charge were the same as inertial mass, we'd be stuck because we couldn't generate electricity really well by having like so like for example like. Wouldn't like you know if someone said oh charge and mass are the same things, that would be really bizarre because they like charge and inertial mass are the same thing, would be bizarre because they work by seemingly completely different ways, right? Inertial mass is just resistance to like mechanical forces. The other one is how it resists to electric fields, and so now we're saying okay I have gravitational fields pulling on something that actually is the same thing as just me pushing manually on like that these principles are indistinguishable from one another.
So is the issue that gravity doesn't choose a force, it chooses an acceleration?
Can think of it this way? Yeah, okay, that's it. You can think of it.
Gravity
yeah.
chooses your acceleration, doesn't choose your force.
It's just you can sort of see
That's
gravitation.
kinda like
Gravity is just acceleration. It's not. If you can okay, you can view it like this. Gravity is just pure acceleration. It's not a force. That's a good way to view it because then the point is, that's
the thing that you can push to.
Sorry?
That's something you can push to talk about for.
Yeah, because, okay, so we're saying now, I cannot distinguish if I'm here, like being pulled down 9.8 meters per second, if I'm in a spaceship. Okay, same thing if somehow I'm in an elevator and the elevator is on the spaceship. If they have the same, if the acceleration there is the same as the gravitational acceleration here, then I cannot distinguish between the two. So in particular, what does that mean? It means that, and this is, I mean, I guess this is probably not done one, but this is usually the like elevator experiment that people talk about. Just that, well, or maybe not. Actually, this is maybe a separate. The point is, so see now we're assuming that what's the cleanest way to say it? Okay, there you go. If I'm here, I'm an inertial observer. I'm not moving. I'm not going anywhere. So if I draw, if there's have laser beams coming out of my eye because suddenly I turn into Superman, the laser beam goes straight, right? Well, if I'm in a spaceship that is going away at 9.8 meters per second squared, that's the same thing as the acceleration here. I cannot distinguish between the two. So Superman on spaceship shooting laser beams out of his eyes, they will go in a straight line for him, right? But now. So next, what happens? Well, if I'm looking at this, what's his name? Zod, like Superman's enemy, is staring outside the spaceship, looking at him fly away. He'll see Superman accelerating. So in particular, what he's going to see, he's not going to see the light of beam going straight because this thing is accelerating. So we'll see the light of beam curving down, right? That's the setup. If someone accelerating a spaceship and he's shooting, I mean, this is only if he's moving really close to the speed of light. Usually it's practically flat. But essentially you'll see the path of the light as being curved because the thing is, this acceleration on the spaceship. So the point is to someone outside of the spaceship, this is what the path of light looks like. So do you buy the path of light outside the spaceship to someone looks like this to someone or not? But then the point is, can
you explain it? Yeah.
So
why the light looks like? Oh, you meant someone on the spaceship that would look like that.
No, someone on the spaceship is a straight line, but someone outside because the spaceship is moving up at the same time. Well, okay, so if the spaceship is moving at a constant speed, then you see a straight line, right? But if the faster the speed, the more vertical the line gets. So the speed is accelerating. Then if initially you're just at rest in front of him, the speed is this. But then as you're accelerating, the tangent gets closer and closer to a vertical line. You get a parabola. Yeah.
Okay.
So, but the point is, see, this is you buy that because if you would, this is believable. This is can be compensated because the spaceship is just inertial force moving it. But the point is, Einstein said now, well, we cannot distinguish experimentally between inertial mass and gravitational mass. So really I'm going to take it a step further and say, well, really the mechanisms are the same. Inertia and the acceleration and pure acceleration and gravity are the same thing. So then this means that this actually also happens if instead of accelerating really fast, it's being pulled by gravity very, very fast. So what does this mean? It means that if I have a really, really large mass, black hole, for example, here, that is pulling this with a huge gravitational acceleration, then it means that light is going to start, we're going to have to have bending again, right? So what did we just say? We really said that the presence of matter is going to curve light. But light, if you're sitting on the photon, I always go in a straight line. Right? Light is moving in constant speed, it's always moving in a straight line. So this is following a straight line in space, but it looks just like a curve. So this is where the curvature of space comes from, the presence of mass. So to summarize this, the physical postulate is inertial, the physical observation is inertial and gravitational masses are the same. So the physical postulate is inertial acceleration and gravitational inertial acceleration and gravitational acceleration are the same thing. So you take that, and again, you just basically do a change of coordinates. Someone is like someone outside the spaceship saying this, and you get that actually matter is the source for curving light rays, so curving space-time. So the point is this coincidence of inertial and gravitational mass gives you, plus a change of coordinate, gives you that matter curves space-time around it. Does that make, not make sense, but does that, let's say, is it okay? Is it clear how the pieces relate to one another, let's say? Okay. So what do we have? We said, so y curvature, this is y, coincidence of masses plus change of coordinate gives us curvature is related to matter. And then, okay, I'll let you go in 5 minutes. Or 2, I don't know. Let's see. What is there still to say? Okay, so I said curvature is related to matter. How do we measure curvature? A simple way is to think about curvature on the plane is what? It's just, the plane is flat. So if I have two lines going away from one another on a plane, the distance between them grows linearly. If I have two lines on the sphere, the distance grows and then comes down, if I have two lines going from the North Pole, the distance between the two lines grows and then it goes to 0, and then as you go around, it grows and it goes to 0 again. And so the distance between the two lines grows, kind of oscillates in this way. And then the third one is if I have, you can have a third type of geometry where, which is, if you look at a hyperbola and lines there, then they always diverge from one another. And so they diverge, they diverge facet and linearly, and basically curvature, this is a really, really rough sketch for why our intuitive notion of curvature, a good way to measure that is the divergence of these straight line, straight with respect to the intrinsic geometry of these spaces. So curvature we can measure by the divergence of straight lines with respect to the space. Okay, good. So now we have the following basically, just in one long line, but one line. How do we get gravitational waves? We're almost there. So matter is related to matter generates curvature of space-time limit, and curvature I can measure that as say divergence. The lines that are straight with respect to intrinsic geometry, they're just called geodesics. They're like great circles and on the sphere and stuff like that. And one way to measure it, one way to measure distance. So to measure distance, how do I measure distances on a sphere? I have to give you a metric on the sphere. How do you find the metric on the sphere? You just look at the inner product locally and you see what that looks like. And then the physicists decided instead of calling it an inner product, we're going to call it a metric, because the really useful thing we get out of it is the distances, the fact that it allows us to compute distances. So the point is, if you look back to the manifold, like defining distances on manifolds, you define first the inner product locally. It allows you to compute angles and distances, and then divergence of. So you can have some. They call these things metrics. Some metrics, say G, and then sort of if I'm flat, my metric is constant, right? But if I'm curved, then my metric changes as I move along a geodesic. And how do you measure how something differs from, say, like how something differs from its average locally, like the local change in something? Well, and this is because of time, a big jump, but I guess for people in analysis, or you know, how do you measure this thing? Well, the Laplacian is a good way to measure how something varies from its average. This is a cute thing. I'm not going to write it, but like, you can actually show just in Rn that like if you take the average value of some function around the point, this is, well, if the function is like smooth or something, yeah, smooth, then this of course looks like utx plus then some correction. And the next order of correction is just the Laplacian and x, and then you have some higher order stuff. The point is, the Laplacian, the moral of the story is, this is just integration in like spherical, not even, this is really simple exercise. But the point is, the Laplacian measures well how a quantity differs from its average. And measuring how the metric differs from its average, intuitively that's related to geodesics, because how the metric differs on average is how these curves are going to diverge and converge from one another. So roughly speaking, divergence of the metrics is this Laplacian on, but the subscript Laplacian of the metric, the subscript m, because it's the Laplacian on the manifold. Okay, fine, but the Laplacian on the manifold, and for gravitational waves, you say matter, let's say equals to 0, you're in vacuum, and you say G is going to be almost flat. It's going to be flat plus some small perturbation. So then matter is related to my Laplacian on the manifold, so I have no matter, I'm in vacuum, so my Laplacian has to vanish of the metric. But the metric I said was just flat, was just some small perturbation from something flat. So this is some small perturbation. The flat metric is just a constant. This is just like you know, in space, the way you measure distances doesn't matter where you are. It's always the same. So this is just the Laplacian on the metric of my perturbation. But remember, distances didn't behave the way we intuitively thought they should in relativity. We actually had this conserved thing. So what this tells us is that this actually, our metric, is not just adding dx squared plus dy squared plus dt squared plus dc squared, say, but it's adding this, like the distances, we add all the spatial stuff and then we subtract the temporal stuff. So what does that tell us then for the Laplacian? Instead of being, say, we'll have say the spatial derivative squared, but then a negative sign for the same reason in front of the temporal derivative. For the same reason I have a negative sign there. This comes from that times h. So if I have space that is almost flat plus some small perturbation, the way that perturbation, the PE that the perturbation is a solution to is, well, this is just a wave equation. But it's really a harmonic. So the perturbation solves a harmonic equation on the manifold, but the manifold, because the metric has this signature where it's like positive in the spatial coordinates but negative in the temporal ones. The harmonic like intrinsic harmonic equation is really a wave equation if we look from our perspective of what x and t are, well, like the spatial coordinates and t are. So, ta-da, gravitational wave, because this is a wave equation and this is our perturbation. And okay, since I don't want to I've brought this for nothing. Here's space-time. Okay. So the point is, now, but this was to illustrate the perturbation. So, like this, if I just hold it calmly enough, this is flat, and then the point is, like, because it's not necessarily, like, what does the perturbation of the metric look like? You know, it's simple things like if I start, like, say, like poking, yeah, this is harder than I thought. If somehow I can hold this and like poke through like that, that's like a small deformation, and then this is sort of what you can have in mind for what H looks like, because the point is now locally around this pinching thing, points like the distances are all messed up. This is gravity. Yeah, I've kept you way too long anyway. So sorry for the mess. It turns out relativity is really confusing.
I'm sure you have a lot.
What's the best relativity book?
I have no idea.
Hello,
If I
is a good one
It's
for
all
special
relative.
relativity.
Just in this big book. Here's a question. How much geometry, I know that mathematicians did geometry before general relativity, right?
Yeah.
Physicists, I imagine, weren't doing much general. They weren't doing different geometry at this point. How much did Einstein know geometry before?
Yes, pretty well.
He did,
Before he came up with this.
Well, like Remond's stuff
His
was
paper.
like Remond's introduction of like Einstein was obviously incredibly like a genius, but he also had decent timing. Like the whole speed of light is a constant. That's Maxwell stuff. That's a few years before. The intrinsic definition of curvature on manifolds. That's Remond, not too much earlier from Einstein. So yeah, he knew that stuff really well, but it was also relatively new development.
Then why did he know it if the physicists didn't really need
No, but
I think-
Einstein was also Minkowski's too.
Yeah, Minkowski derived every math,
Actually,
all the math
when they
before
told
Einstein.
Minkowski what Einstein had done, he said like the idiot was sitting in my class.
So he was a mathematician. He was taking class. He was doing things that physicists weren't normally doing.
Well, the physicists in Germany normally do.
Physicists in Germany were learning differential geometry before
They
general
still
relativity.
do. Like,
Well, obviously they still do because this is important. Before this, I'm asking if they were learning geometry.
yeah.
Really?
Yeah.
I don't, yeah.
Yeah, I think like that class that he took was not math, it was like part of the physics pencil.
So the paper of general relativity, one of the first is like what, 1905?
It's 1905 is like special
1905.
and general.
Yeah, and so it's full of differential geometry.
Sorry?
I think that paper is
Yeah,
full
well,
of.
I know
So-
when he developed the theory, he had to have geometry, but I don't know if he like realized he needed to
Wasn't-
learn geometry and then went and learned it from other mathematicians, or whether he knew it and he just like, finally I could use it for something.
The guy who gave his name to the like Calabi-Yau manifolds who talked to Ted the other like year said that he found a guy who told him the differential geometry. So I don't know. This might be focal there.
Okay, I don't know.
But I think that guy might know his stuff. I don't know.
I guess he understood the connection between the things and he went and like said, okay,
One of
I'm
the
gonna
things,
use this.
like apparently, I mean, I don't know how much of this was, but like he would, like as a kid, Einstein would have things like, what would it look like if I were sitting on a photon and like going the speed of light, like stuff, like, there's a lot of it that was asking the right questions, and why did he have the tools for it? I think he got a bit lucky in terms of being around people who were talking about this more than others at that time. I don't think the stuff he knew about geometry was like standard undergrad curriculum in math at the time. Yeah.
Yeah. What's the perturbation people observe early this year? Because I'm thinking like, how could I observe perturbation come up all of a sudden in the
Yeah,
universe?
so what they did is basically they had like really long laser beams and
That's a man-made perturbation?
Oh no, oh sorry, where the perturbation comes from?
Yeah.
Oh, like two humongous black holes crash into another.
But how could they
That's why.
predict that there's such perturbation? Well,
What do you mean?
You
How-
cannot predict it, you can just observe it.
okay, okay. I kinda know. Okay.
Yeah, they didn't predict where it was going to happen.
Okay.
They just, because when you observe stuff, you observe stuff that happened like billions of years ago. So they just saw something happening, and they saw it happening before they got perturbation coming towards them.
Okay.
Like, yeah.
Wait, sorry, just about that last point. Does the perturbation also travel at the speed of light or
I
not?
don't know. I really wanted to
Because
find a good answer.
if it-
I'm not-
if it-
I don't exactly-
if it does travel at the speed of light,
is it
then-
speed of light? Okay.
Then you can't know beforehand.
No, but they
You
can
could
see
only
them.
have
They
set-
can,
set
yeah,
up
but they can
for
see them going towards one another, right? Yes, you're right. Yes, you're right. Yeah, it definitely doesn't go fast into the speed of light. That's for sure. But
So they see this cosmic disturbance and they think, oh, that might be causing gravitational waves hitting us right now.
yeah, well, I think in this case it's something like they see like two universe thing like spinning, like two really massive black holes spinning and going toward each other, and say once they collide, something should come our way. I think that's roughly, because, you know, when you say like small perturbations, yeah, but you still have it's small, not on
So like when you have that equation, right, you're solving like time backwards, but how do you know that it's exactly like 700 billion years ago at that point that the signal is coming from 700 billion years ago in from a like, very huge collision of particle system instead of like coming from like just 1 second ago but from a very small station.
Oh, okay, yeah, well then you're asking were they careful enough and like isolating their experiment, right? Sort of like, is that so? Like you don't want your detectors to be set up by an earthquake nearby, this sort of thing. That's what you're.
Not exactly, because like in the published result they say that okay, we observe this signal and it comes from several billion years ago and from two black holes of this mass and that mass, right?
Yeah.
And but when you solve that equation, actually like you get a time invariant transformation, right? So why not this the signal comes from just a second ago, but from a really small scale collision that's of like really small mass.
Well, in order to perturb the space-time, you need quite a lot of energy. I don't think you can do, like an earthquake doesn't really